Okay, so if you are looking at this not with NK delta T kinds of things, but if you're more into the molar kind of world, looking at number of moles as compared to actual numbers of particles, then the specific heat that you're going to calculate, this is going to be the molar specific heat. And instead of having 3/2 NK delta T for the internal energy, it'll be 3/2 R little n delta T, where R is the gas constant and N is the number of moles. So when we do the cancellation, the molar specific heat will be 3/2 R, right, for any ideal gas, if we're doing a constant volume process. All right? So now what we want to do is look at the other line, right? We're going to do a constant pressure process, an isobaric process. What is the specific heat for that process going to be? All right? So next we'll go over, we'll erase this, we'll take a look at that. All right, so up now for this specific heat with constant pressure process, right? So it's going to go exactly the same way. We are going to do the first law of thermodynamics, right? You barely can maybe see it right here. I'll just kind of delta U equals Q plus W. And I want to emphasize something here, that this is Q on the system. And this is work done on the system. All right? So now what we're going to do is think, first thing I can do here is exactly what I did before, only correctly this time. So what is the internal energy for an ideal gas? Right. 3/2 NK delta T. Right, I forgot the N the last time. So there it is this time. All right. So this is going to be Q, the amount of energy supplied through heat into the system. And again, as we had before, you can't see it, it's way over there on the blackboard, that's going to be NCP delta T, right? The number of molecules, the specific heat for constant pressure process, times this change in the temperature, plus the work done on the system, right? And now for the emphasis of this on the system business. Okay, and so now, why emphasize this work on the system? Well, let's think back to this work business, right? We had this cylinder with a piston, and the work, right, got to move the piston. The pressure inside produced this motion. All right? Now notice, this is not the world, the universe, doing work on the gas. This is the gas doing work on the universe. Right? And that is what we see when we have this pressure volume plot. We have some process that goes from here to here. We do the area under the curve. This is what's going on here. This is work being done by the gas on the rest of the universe. So it's going to come into this equation with a minus sign. If this is work on the system by the universe, what we've determined here is work that the system does to the universe. Right? It's now doing work to everything else. And so it comes in with a minus sign. Right? So that's the first thing that happens. This will be minus the work the system does. So in fact, let me just write that down. So we have 3/2 NKB delta T equals NCP delta T minus work done by system, all right, on the rest of the universe. Okay, and now what we're going to do is we're going to look at this constant pressure process. And this one is easy, right? Look, here is our process, right? There's the area under the curve of this process. It's simply the delta V times the pressure. And so I can put that in right here, right? So this now is 3/2 NK delta T equals NCP delta T minus P delta V. All right? So now we've got an equation that has stuff with regard to the gas. The problem is we got this delta V business in here. Remember before, what happened is we had delta T's everywhere, we canceled them out, so we would get a constant that isn't a function of temperature, right? If something's hanging around, this constant is not a constant. If T or P or V hangs around, ooh, that's not a constant. So, we'd like to get rid of this, and there's a way to do that, all right? So let me give myself some more space here. And what we're going to use is the fact that this is an ideal gas. So we have PV equals NKT. All right? So this is a constant pressure process. So V equals NK over P. Right? We could do this whether it was constant pressure or not. But I'm setting this up because I know what's in the parentheses is a constant. So if I'm going to look at certain spots, certain states the system is in, let's say the final state, the final volume will equal NKB over P, this is a constant, times that final temperature. Likewise, the initial state is NK over P times T initial. Now subtract the bottom equation from the top. I get delta V, V final minus V initial, equals NK over P times delta T, T final minus T initial. Now swing the P back over. I have P delta V is going to be NK times delta T. And now you see how I get rid of the P and delta V in the equation over here. I make this substitution. All right? See, it's nice that this is taped, because I don't have to give you stories to give you a chance to catch up with my writing on the board. You can always stop the tape, catch up, then move forward. So I shouldn't have gone through that because it was just time for you to catch up. So anyway, right here we've got 3/2 NK delta T equals NCP delta T minus, now I've got NK delta T, right? Obviously the N's will go away. Obviously the delta T's will go away, right? And I have 3/2 K. Let me bring this K over plus another K equals CP. Or CP equals 5/2 K. Now we see what the specific heat for a constant pressure process is. Remember, specific heat for a constant volume process was 3/2 K. For a constant pressure process, it's 5/2 K. Let's stop for a minute and think why. Well, in the constant volume process, we are using all the heat energy to create the random motion, right, to change the temperature. All right? It all goes into delta U if there's no work here. Right? It all goes into delta U to change the temperature. 3/2. Now, when we have a constant pressure process, the same amount of energy goes into increasing the temperature. But we have to supply some extra heat energy for the system to be able to do work. See, here's the important thing with this. I'm supplying heat energy. It's now going into 2 bins for the constant pressure process. One bin increases the internal energy of the molecules. The other bin is what the system uses to do work to the outside environment, to move the piston that's keeping the thing at a particular volume, right? And so it has to do work to move that piston. That work had to come from somewhere. It came from the other K term, K part of the specific heat, right? So now we see we've got the 3 different specific heats. One for solids and liquids, where it depends upon the material. It doesn't depend upon how you make the process occur. It simply depends upon the material. The other change temperature with heat method, right, is specific heat again for an ideal gas. Now it doesn't depend upon gas. The ideal gas says, I don't care what kind of material, what gas it is. It's simply an ideal gas. Okay? Now I've got to worry about these 2 different processes for getting me from one temperature to another temperature. The constant volume process, the constant pressure process. Those 2 have 2 different specific heats that we've determined. The constant pressure process, 3/2 K. The constant volume process, 5/2 K. All right, so we've gotten the specific heat stuff down. Now, what I want to do is move on to another piece, and that piece is about how we reach thermal equilibrium when we have 2 different pieces of material or 2 different gases. All right, so that's the next section. So I'm going to erase the boards and get to that.